Hi, everyone. Thanks for joining this session. In this talk, we'll have a look at combining a supervised learning rule, backpropagation, and one of the unsupervised learning rules to see how they work in a classification task. The purpose is to take a beginning step to see whether we can find a better learning rule to address the credit assignment problem, which is how does the brain adjust the synapses of individual neurons to support learning, and how do we adjust the weights in the artificial neural networks to produce a desired outcome with respect to our objective. And the current most and sort of only efficient and scalable solution to this problem we have in machine learning is backpropagation. And it has been shown that backpropagation can be approximated by the brain to some extent, at least in the feed-forward network. But backpropagation has some problems. For example, it is prone to forgetting, especially in an online learning setting. And the network can be biased towards texture when recognizing images. And it is vulnerable to adversarial attack. On the other end of the spectrum, we have fully unsupervised learning rules that we know is going on in the brain. For example, various forms of Hebbian learning. When combined with some other mechanisms, Hebbian learning can learn some interesting things. For example, if we take into consideration the competing between neurons, it can capture the input statistics. And if we add the inhibitory recurrent connections, we can construct a network to match similar input to similar output. But the biggest problem with these fully unsupervised learning rules is that they don't scale up to big networks and complex problems. So there has been work looking at augmenting different forms of Hebbian learning with other algorithms. For example, if we can determine the strength of each individual Hebbian plasticity in a network, we can get an agent that can learn to walk quickly from random weights. And if we augment the network trained by standard backpropagation, so we add a Hebbian plasticity term to the weights controlled by backpropagation, and we can get networks that perform better at tasks, for example, a fast memorization of images or navigation through maze compared to a non-plastic network. So in this work, we're looking at another way of combining backpropagation and unsupervised learning rule, which is we add the implement these two learning rules simultaneously, and within a mini batch add the updates of backpropagation and unsupervised learning together with their respective learning rates. And the unsupervised learning rule we used here is introduced by Krotov and Hopfield. It is an extension of Alha's rule with a Hebbian term and a regularization term of the weights. And the rank function implement the competing between the neurons. So for a specific input, only the neurons that are most activated get updated by the Hebbian learning. And the neurons that are also highly activated but not most activated get surprised by a small anti-Hebbian learning. And the rest of the neurons are not updated. So we test the performance of these different learning rules in a two-layer network on CFA10. The first layer is a convolutional layer, and it has 5 different settings. The first fixed unsup is we train the weights fully using the unsupervised learning rule. Then we fix the receptive fields and only train the readout layer. And fixed random is we fix the first layer randomly and train the second layer. And similarly, innate unsup is we initialize from unsupervised learned kernels and then train the two-layer end-to-end. And innate random is when we initialize the first layer from random, which is the standard backpropagation setting, and the BP plus and super is the combined learning rule. As we can see, the classification performance is kind of similar in all these cases, but if we add in the unsupervised learning components, it doesn't quite reach the highest performance of the standard backpropagation. So let's have a closer look at the representations learned by different learning rules to see why might this happen. So as we can see, backpropagation doesn't actually change the receptive fields much. If we initialize randomly, it still remains random. And if we initialize from the unsupervised trained kernels, there are some small changes of weights, but it's barely perceptible if we compare this one and this one. And so if we use the combined learning rule, we get the receptive fields look like the mix of the random weights from the backpropagation and the structured weights from the unsupervised learning. Because there are also these more random looking kernels that are not fully trained by the unsupervised learning rule, let's have a look at whether there is a difference between the usefulness of the random kernels and the structured kernels to the classification. So we calculate the contribution of each kernel to the correctly predict class using an algorithm called layer-wise relevance propagation. As we can see, the blue curve is the standard backpropagation. So the random kernels are more or less contributing equally. And the orange curve is when we initialize from the random the structured kernels. It results in a sparser contribution, and it seems to be indicating that the structured kernels are less able to get used by backprop for the classification. And if we look at how much the kernels change after training, we can see that the random kernels tend to get picked up by the backpropagation and changed more. So it seems to be seeing that the structured kernels is just not as useful as a random projection for the classification task. But if we look at the transfer performance of these different learning rules, that doesn't seem to be the case. So if we train the network on 8 classes using the 3 different learning rules, the backpropagation, the combined, and the unsupervised learning rule, then we fix the first layer as the receptive fields learned by these rules, and then fine-tune the second layer on the 2 holdout classes. We can see that, so although the unsupervised learning rule results in a slightly worse performance than the standard backpropagation, it actually performs more or less the same on the holdout classes. So which is indicating that the unsupervised learned kernels actually is useful and can better transfer between the classes. So for a summary, when we deploy these 2 learning rules in the classification task, we can see that when we're doing it simultaneously, the unsupervised Hebbian learning isn't completely disruptive to the backpropagation. The backprop can quickly adapt to the new weight space after each update. And the changes due to the backpropagation can be really small compared to the changes due to the Hebbian learning, which means the supervised changes or the top-down influence may be hard to identify experimentally. And we can also see that the unsupervised Hebbian learning is slightly hindering the efficiency of BP. The structured receptive fields result in a sparser contribution, and they are, compared to the random ones, they are less likely to be changed by the backpropagation. So we can see that there are obviously benefits to be reaped from these 2 different learning rules. One is more efficient for specific downstream task, and one capture the richer statistics and have better transferability and can take use of the constant incoming without the supervision signal. But simply adding these components together seems to be contradictory to each other, and we need to find a better way to combine these supervised and unsupervised updates to get a more efficient combined learning rule. So that's it. Thanks. I'm happy to take any questions.
Thank you, Ada. That was wonderful. Here's some applause from everybody in the audience. All right, so if you have questions, please type them in the Q&A, or if you just want to raise your hand, and I'll put you up as a panelist and you can ask your question directly. In the meantime, let me ask you, Ada, do you have any ideas about, what kind of tasks or situations may allow for the two learning rules to actually, result in better accuracy or better performance overall?
Yes. So in terms of the tasks, if we're considering a simple classification task, we can more or less be sure that there is no better performance than backpropagation. So when we were talking about the learning rules, we also need to take into consideration of our objectives. So for example, if we want to not only do a classification, but also able to construct what we see or predict what we see next. So if we, and also during real life learning, the learning also often happens in an online way. And so we don't have the data available for batch training. It's just a series of tasks that comes one by one that may have different distributions. So in these more complex objectives and complex learning scenarios, I think we might see an advantage of the combined learning rule to the simple backpropagation.
Very interesting. Thank you. So we have a quick question from Kirubel Danieli. He actually typed it in the chat only to the panelists, so the audience can see it actually. But the question is there a reference for this work? Great talk. Is there a reference?
Yes. So
maybe if you have a reference, you can just type it afterwards. Maybe you can just say.
Yeah, I'll type it in the chat.
Yeah, type it in chat maybe afterwards. Okay, so we have another question in the Q&A, and this is from Tehere. Tehere is saying, thank you. Have you looked at how these mixed learning schemes are compared to backpropagation in terms of those shortcomings of backpropagation you mentioned in the beginning? For example, adversarial robustness.
One of the reasons like backprop is so vulnerable to the adversarial attacks is because if you're just following the exact gradient, basically backprop finds the like the least effort way to solve your objective, and it may just result in capture a very like trivial feature that doesn't quite make sense to human eye, and rather than capture the real properties of certain, for example, image classes. So if we are using a combined learning rule, the unsupervised part has a better capacity to capture the statistics of the input, and and also without the exact gradients, we may have a more smoother landscape, make the network that's more resistant to adversarial attack.
All right, thank you. Tehere, do you want to follow up?
Yeah, thanks for the question.
Okay, wonderful. Well, thank you, Ada. So here's some applause again from the whole audience. All right, so let's move on.